Across fields and kitchens, starch is one of Earth's quiet stores of captured sunlight. It sleeps inside wheat kernels, rice grains, potatoes, maize, and cassava roots. Under a microscope, starch appears as pale granules, compact as tiny sealed vaults. Each granule holds long sugar chains, folded tightly by the plant. For plants, this stored energy is a pantry against darkness and winter. For people, it became bread, porridge, noodles, beer, and daily comfort. But starch was not simple sweetness already waiting on the tongue. Its sugars were locked in chains too large for taste to recognize. Grinding could break kernels, yet the hidden sweetness often remained stubbornly bound. Heat softened the granules, but time still moved at an old pace. Long before laboratories, seedlings solved this problem in the damp spring soil. A germinating grain releases amylases to feed its first root and shoot. Fungi found another path, searching fallen seeds, wet leaves, and forgotten grain. Their fine threads enter starchy food like patient explorers in a forest. Among these fungi, Aspergillus molds became especially gifted readers of stored starch. On cooked grains, koji mold turns stored starch toward fragrance, sweetness, and life. East Asian brewers and cooks trusted this transformation across many generations. They did not see fungal alpha-amylase, but they knew its signature. In 1811, Gottlieb Kirchhoff watched malted grain change starch into sugar. His observation hinted that conversion could happen without living yeast or magic. 2 decades later in Paris, Anselme Payen and Jean Pessoz pressed further. In 1833, they named a starch-splitting substance diastase, meaning separation. Diastase became one of the first enzymes recognized by modern science. A hidden worker had stepped from kitchen mystery into chemical history. Yet early diastase mostly came from sprouting barley and prepared malt. The fungal answer still waited inside old koji traditions and quiet workshops. Jokichi Takamine grew up between Japanese fermentation craft and Western chemistry. He saw that koji mold could make remarkable diastatic preparations from grain. In the 1890s, Takamine brought this insight into industrial enzyme history for the wider world. His fungal diastase came from Aspergillus oryzae, the familiar koji mold. It helped prove that microbes could supply useful enzymes beyond malted grain. Later vocabulary named this starch-cutting activity alpha-amylase, a cornerstone of gentle starch work. A fermenting room mold had entered laboratories, medicine cabinets, and modern biotechnology. The enzyme's task is modest, opening starch without fire, force, or drama. Picture a chain of sugars, bead after bead, bending in water. Fungal alpha-amylase settles onto the chain like a careful, unseen hand. It snips links inside the chain, making long molecules shorter. These fragments become easier for other enzymes to finish into sweetness. Nothing is smashed. The change is selective, small, repeated, and almost silent. In dough, this quiet cutting releases sugars for yeast to share. Yeast answers with bubbles, and bread begins to lift itself. The crust browns more readily when hidden starch becomes available. A loaf carries chemistry as softly as it carries steam from the oven. In breweries, amylases help grain starch become fermentable sweetness for yeast. In starch kitchens, they help prepare syrups, fillings, and gentle sweeteners. In textile mills, enzymes help remove starch size from woven threads. Cloth can be cleaned with less reliance on caustic chemical treatment. In paperwork, starch adjustment helps fibers carry strength and finish. In animal nutrition, amylases can help unlock grain energy more completely. In flour correction, fungal alpha-amylase helps bakers manage variable harvests. Everywhere, the pattern is the same: access instead of destruction. The enzyme opens what is already present rather than adding strangeness. Fungal alpha-amylase is valued for calm work in warm, watery mixtures. It belongs to a larger amylase family shared across living nature. But the fungal branch carries the memory of mold on grain. Its history links fields, fermenting rooms, pharmacies, bakeries, and mills. Takamines' discovery also changed how people imagined industrial biology for the next century. Factories did not need only smoke or pressure and heat. They could also borrow the delicate tools of living cells. That idea now guides greener making, from food to materials. An enzyme can replace steps that once demanded harsher conditions. It can save resources by making transformations more precise and targeted. It can turn agricultural starch into value with fewer burdens. It can help industry listen to biology instead of overpowering it. And it reminds us that innovation often begins with attentive observation. A sprouting seed, a moldy grain, a patient chemist, a baker's loaf. Together, they reveal a technology older than industry itself, again and again. The smallest tools can quietly alter the largest material flows. Starch will keep returning with every harvest and season, feeding cities and soils. Fungal Alpha-Amylase carries an old fungal wisdom into a low-waste, sustainable future. Enzymes Bio is run by people who believe enzymes are the future of clean industry. So we built one platform for startups, labs, and makers to source them without the usual hassle. Gentle on the planet, built for what's next. Visit Enzymes Bio.